Okay, so we will continue with part C of section 4. Okay, the section 4 is matrix operations. Matrix operations. Okay, operations. Section C. Section C is mechanics of matrix multiplications. Mechanics of matrix multiplication. Okay. Okay. So let's start with this definition. Yeah. Here, this video is going to be a bit long, okay, because we have several concepts to cover, and for each concept, I will try to give a small, quick example, okay. Then in the next video, I will do a big tutorial, okay, but this one is going to be a bit long. So let's start with the definition. A matrix. A matrix with all zeros except for one in the ij. So all zeros except for one, okay, in the ij, entry, except for, let me go here, except for ij, except for one in the ij entry. In the ij entry is an ij unit matrix. Is an ij unit matrix. So basically we have just given the definition of a unit matrix, okay. Unit matrix or matrix unit, or matrix, simply matrix unit or unit matrix. Okay, so example of an ij, so maybe a 2 3 unit matrix is okay, so all zero. So let's say we have 2 rows and 3 columns, 1 2 3. So for this matrix is 2 3. Okay, so we have second row, okay, second row and 3 columns, so, and the second row and third column. So 1 here, everything is 0, okay, except for 1, okay, in the matrix, and the 1 is in the 2 3, okay, third row, second row, 2 3, so second row, third column. Okay, this has been a very long day. So let's do a small remark here. Remarks. Okay, so we are going to multiply an ij unit matrix from the left. Okay, so I'm going to write small 1 here. Okay, so I'm going to write acting from the left. Okay, an ij matrix, an ij unit matrix copies row j, copies a row or jth row j of the multiplicand into row I. Row I. Okay, of the rest. Okay, let's have a look. Example. Okay, ij example. Okay, we can go for both. Yeah, it doesn't matter. We can go for ij or example ex. So let's say I am going to have this 1 2 unit matrix, so 0 1 0 0 0 0. Okay, so I'm going to multiply that matrix with the following matrix: 3 2 5 4. So this is a 3 by 2 matrix. This is a 2 by 2. So the answer is going to be a 3 by 2 matrix. Okay, so this multiplication is defined. So it says that it will copy. So this is we have okay. So the matrix is defined, and this is an 1 2 unit matrix. So ij. So what the definition says, or the remark says, that if you multiply from the left, okay, it acts on the rows. So basically, from the left, it acts on the rows. So as you can guess, from the right, it acts on the columns. So here, it says that it will copy the j row into the row I. Okay, it will copy row j into row I. So it will copy row 2 into row 1. So row 2 into row 1. So basically we will have row 2, okay, into row 1. So let's have a look. Let's see. Let's actually go with the matrix multiplication first. So we will do dot product of the row from the left multiply with the column on the right. So 0 times 3 is 0, 1 times 5 is 5. Okay, now 0 times 2 is 0, 1 times 4 is 4. And yeah, 0 times, okay, so yeah, 0 times 0 plus 0, 0 times 3 plus 0 times 5 is 0. 0 times 2 plus 0 times 4 is 0. Here, the row 0 times 3 plus 0 times 5 is 0. 0 times 2 plus 0 times 4 is 0. And let's check if that's true. The definition says it will copy row 2 into row 1. So row 2 is 5 4 into row 1. So 5 4. Yeah, exactly. That's the. Okay. So let's do acting from the right, as you can guess. Okay, it copies the columns. Okay, so it acts on the columns too. Acting from the right, an ij unit matrix copies column I, column I of the multiplicand into column J. Into column J of the result. The result. Okay, so example. Let's have the following matrix: 2, 1, 4, 3, 6, 8, and 7, 5, 9, multiplied by yeah, the same the same ij unit matrix. So 1, 2 unit matrix, 0, 1, 0, 0, 0, 0. So it says it is going to copy. So this is 1, 2. So it's this time it's going to copy column 1 into column 2. So basically, if we do the multiplication, we will see that it will copy column 1 into column 2. Let's do the multiplication and then see if that corresponds. So we are going to do the dot product between the row of the left hand side and the columns of the right hand side, and I'm going to fly through it quickly. Okay, so 0, and here we are left with 2. First of all, this is a 3 by 2 matrix, and this is a 3 by 3 matrix, the first matrix, and 3 by 2 matrix. So the matrix is the matrix multiplication is defined. Okay, we are going to have a 3 by 2 matrix. So here we have 0. Here we have 3, 0, and 7. Okay, if you multiply them, and the definition here says that it is going to copy column 1 into column 2. So column 1 is 2, 3, 7. So as you can see here, it copies it into the second column. Okay, so another remark, number 3, rescaling unit matrix. Okay, so the rescaling unit matrix, or matrices. Okay, what does it do? It simply rescales the result. It simply rescales the result. So yeah, the result. Okay, so let's have a look here. We are going to instead of a unit matrix, we are going to have 0, 2. We are going to have 2 there, and as we said, it is going to copy the second row into the first row and multiply it by 2. Okay, and let's multiply this with a 2 by 2 matrix. 3, 2, 5, 4. Okay, this matrix here. So basically it's going to copy row 2 into row 1 and multiply it by 2. Okay, so basically let's have a look. This is, I'm going to go quickly through matrix multiplication. Okay, that's going to be 10. This is going to be 8. Okay, this is going to be 0, 0, 0, 0. Okay, so let's have a look. Our second matrix. Okay, because this is a 1, 2. matrix, unit matrix. We can say unit because the two is not the two is different from one, so it's two times one two unit matrix. So it's going to copy row two into row one. So row two here is 5 4 into row one, yes, and then multiply it by two. So 2 times 5 is 10, 2 times 4 is 8. Okay, so let's continue. Okay, so we have here another remark. Maybe let me go to next page. Another remark. 4. Number 4. Okay. Matrices with two non-zero entries. Okay. So matrices. Okay. So with the matrices with two non-zero entries, and here I'm going to have a small a here. If the left multiplier has okay, so let's continue here. If the left multiplier has entries in different rows, then the actions don't interact. Okay, if the left multiplier has entries in different rows, then their actions don't interact. Okay, so I think I should highlight. Maybe I should say different rows and don't interact in different colors. Okay, in different rows, then the actions don't interact. Okay, so let's have a look. Let's have an example here. So let's say we have this matrix. Okay, 1 0 0 0 0 2 0 0 0. Okay, multiply by 2 1 4 2 1 4 3 6 8 7 5 9. Okay, so here we can split this matrix, big matrix, into two, right? We can split it into 1 0 0 0 0 0 0 0 0, okay, plus 0 0 0 0 0 2. This is a rescaling matrix. This is 1 1 unit matrix. This is Second row, so it's 2, 3 rescaling matrix, okay, and all of them multiply by okay, all multiply by our matrix. And if you remember, we have said that matrix multiplication distributes over addition. Okay, 2, 1, 4, and 3 is 6, 8, and 7, 5, 9. Okay, so this is the same as saying that 1, 0, 0, 0, 0, 0, 0, 0, 0 multiply by the matrix. So let's distribute over addition. So we have 2, 1, 4, 3, 6, 8, 7, 5, 9. Okay, plus here the rescaling matrix is 0, 0, 0, 0, 0, 2, 0, 0, 0. So there is 1 0 mixing here. 0. 0. And here we have 2, 1, 4, 3, 6, 8, 7, 5, 9. Okay, so what have we said? That if the unit matrix is multiplying from the left, it copy the j row into the I column. Okay, so here we have the unit matrix is 1 1, so actually it does nothing to this matrix. Okay, sorry, I won't say it does nothing, but it just copy the first row into the first row, so it just keeps the first row. So we have 2 1 4 and then 0 0 0 0 0 0. Okay, plus here it will copy. So here we have a second row, third column. It will copy the third row into the second row and then multiply it by 2. So let's copy the third row into the second row. So this is 0 0 0, so it's going to be in the second row and multiply it by 2. So 7 5 9 multiplied by 2 is 14, 10, 9. Okay, and the third row is 0 0 0. And let's do the addition and see. So we have a 2. So you see they do not interact. So let me write it here. The final, okay, now so the final answer is we have here 2 1 4. Okay, we have seen how to matrix sum. We do the sum entry wise. Okay, entry by entry. So we have here 2 1 4, 14 10 9. No, 2 by 9, 2 multiplied by 9 is 18. Okay, so this is 18. Okay, this 2 is 18, 18, and the rest is 0 0 0. Okay, so as you can see, the actions do not interact. Okay, so now let's check if that is true. Okay, so let's actually do this product by just doing a matrix multiplication. Okay, so this is going to be 2. That row multiplied by the second column is going to be 1 here. This row multiplied by the second column is just, we are just going to keep 4 there. Second row multiplied by the first column, we have 14. Okay, second row, second column, 0 0 0. 2 multiplied by 5 is 10. And the second row multiplied by the third column is 18, and 0 0, so it's 0 0 0. You see, this is the same. This is the same as this. Okay, now let's continue with this remark. Okay, so we have 5. If the entries are not in different rows, so they are in the same row, then their interaction then the actions do interact. Okay, so matrices, and matrices with two non-zero entries. Okay, so if the left if the left uh, multiplier has entries in the same row, then that row that row of the result is a combination. So basically it means the actions to interact. Okay, is a combination. So let's have this time. Okay, our left multiply is 1 0 0, sorry, 1 0 and 2. Let's put the 2 on the same row, 2, and here 0 0 0 0 0 0. 2 1 4 3 6 8 and 7 5 9. So what are we going to do is we are going to split the left multiplier into two matrices. Okay, smaller matrices. So we have 1 0 0 0 0 0 0 0 0 plus 0 0 2. This is a rescaling matrix. 0 0 0 0. Okay, all multiplied by 2 1 4 3 6 8 7 5 9. Okay, so as we have said, it's going to distribute, okay, over addition. Okay, I'm taking time to write all these baby steps because this is our first time of doing something like this, of viewing these concepts. Okay, 2 4 3 6 8 7 5 9. Okay, then multiply by the second matrix is 0 0 2 0 0 0 0 0 0, multiply by 2 1 4 3 6 8 7 5 9. So we know that okay, multiplying from the left, we are just going to copy the first row, 2 1 4. Okay, all the other rows are going to be 0 0 0. Okay, so those are zeros. 0 0 plus here, this is 1 by 2, 1 by 3. So it's going to copy the third row into the first row and then multiply it by 2. So the third row is this, you copy it into the first row and multiply it by 2. So the third row is 7, 5, 9. So we have 14, 10, and 18. Sorry. And the two other rows are 0, 0, 0, 0, 0, 0. Okay, so what is going to be the final answer? We said that they do interact. So first of all, the other two rows are going to be 0, 0, 0. And the top row, the first row, is going to be the entry by entry sum. So we have 16. 1 plus 10 is 11, and 4 plus 18 is 22. Okay. So let's check this with a normal matrix by matrix multiplication. So let's see here, we just want to do matrix by matrix multiplication. So 1 is 0, 3 multiplied by 3, 2, 7. This is going to be 2 plus 14 is 16. Here we have 1 plus 10 is 11, and here we have 4 plus 18 is 22. Okay, and then a 0, this row is 0 multiplied by all the columns is going to be 0, 0. The third row is also just 0 multiplied by all the 3 columns, so it's going to be 0, 0, 0. So yes, it is verified. Okay, let me double check there. So as you can see, this is going to be similar. Okay, similar for columns. So let me say note, it is going to be similar. 4 and 5 is going to be similar. Okay, 4 and 5 operations. Okay, if multiplied from the right, it is going to act on the column. It is going to act, if multiplied by from the right, it is going to act on the columns similarly. Okay, so let's have a look. We have two here remark. So the next is going to be a lemma. Okay, so number 3. Let's have a look at this lemma. Okay. The lemma says, in a product of two matrices G and H, the column of G, H are formed by taking G times the columns of H. Okay, this is very intuitive based on everything you have done so far. In a product of two matrices G and H, the columns of GH are formed by taking G times the columns of H. Okay, so basically we are going to have G times the columns of H. So multiply from the left, they act on the rows. Okay, so basically we have dot 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 H1 dot 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 HN dot 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 dot. Okay, it's going to be equal to G. Okay, so it's going to act on the rows. So it's going to be G times H1 dot 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 G times HN. So dot 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 and dot dot dot. Okay, and the rows of GH are formed by taking the rows of G times H. So now it's going to act from the right. Okay. Basically H is multiplying G. Okay, so it's going to act on the columns. Basically everything we have just said so far. So we have dot 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 G. Okay. 1, 2, 3. GR. Okay. Times H equals, okay, G 1 times H G R times H. Okay, so okay, let's continue with as I said, this is going to be a very long, okay, a bit long tutorial. Definition. Okay, the main diagonal or also called principal diagonal or principal diagonal or just simply diagonal. Okay, just diagonal or diagonal okay of a square matrix goes from the upper left to the lower right. So this is the example. Okay, let me give you this 3 by 3 matrix. Let's say you have 1 1 a 1 1 a 2 1 a 3 1 a 1 2 a 2 2 a 3 2 and a 1 3 a 2 3 and a 3 3. Okay, so the diagonal or the main diagonal or the principal diagonal is this, is a11 a22 and a33. That's the diagonal. Okay, so let's continue. 5, have a look at identity matrix. and identity matrix is a square and every entry is zero except for one in the main diagonal. Okay, that's the identity matrix. Is zero except for ones in the main diagonal. So here is an example. Again, I'm missing EX and EG. So this is an example. So you have 3 by 3, 1 is 0. 0. Oh, let me give you a formal representation. So you have, it's called INN, okay, which is 1 0, okay, and 0 there, 0 1, this is 0, okay, dot 0 and 0 and 0 dot and 1 there, and yeah, we have okay. So okay, let's have a look at this remark. As I said, this is going to be a bit long. Okay, a bit long video. So remark, small remark here. Remark. Okay, identity matrices have their multiplicand unchanged. Okay. So identity matrices have their multiplicands unchanged. So basically, let's see. Okay, let's say we have. Let me give you this example. We have 2 1, 3 6, and 7 5 multiplied by this 2 by 2 identity matrix. 1 is 0 0 1. Okay, so basically it's going to leave the multiplicand unchanged. So that's multiply from right. We can do the same thing by multiplying the identity matrix with the multiplicand from the left as well. Okay. Okay. So we have let's do normal matrix multiplication. 2 by 1 is 2, and plus 1 by 0, so it's just going to be 2. So 2 1, the row multiplied by this column is going to be just 1. We have 2 3 3 6 multiplied by 1 is 0, is just going to be 3. And then we have 3 6 multiplied by 2 0, this is going to be 6. And here 7 5 multiplied by 1 is 0 is 7, and 7 5 multiplied by 0 1 is just 5. So as you can see, yeah, we still have our multiplicand. Okay, whether multiply from left or from right, it will it will leave the multiplicand unchanged. Okay, so let's continue with this definition. So definition, diagonal matrix is square and has 0 of the main diagonals. Okay, so diagonal matrix is square and has zeros of the main diagonal. Okay, so basically we have something like this: a 1 1 0 0 0 here, a second row, second column, 0 0 0 and a n n. Okay, so continue on the next slide. So number 8 definition. Okay, and nearly there. A definition. Okay, so a permutation matrix is a square and is all zeros except for a single one in each row and column. Okay, so let's give an example. Okay, where I'm going to multiply from the left. Okay, so this is example. Okay, so we have 0 0 1 0 1 0 and 1 0 0. Okay, this is a permutation matrix. We can decompose this matrix into simpler matrices, which are unit matrices. Okay, so we are going to multiply that matrix. So this is example 1. Okay, I'm going to give you only one example anyway. So multiply by 2 1 4 3 6 8 7 5 9. Okay, so let's multiply this out. Or first of all, let's see what it should do. Okay, so if we take this first unit matrix, so 0 0 1, this is a 1 3 unit matrix. Okay, so it is going to copy the third row into the first row. Let's do it. So third row, 7 5 9. Okay, and it's going to copy the third row into the first row, and then the second row here we have what we have a 2. Okay, for the second row I don't have space here, so let me write it here. A 2 by 2 unit matrix. Okay, so it's going to copy the second row, so it leaves the second row there. Okay, so 6, 8, 6, 3, 6, 8. Now the third row is third row, first column, so it's going to copy the first row into the third row. Okay, so it's going to copy this row. So 2, 1, 4. You see, this is a permutation. It permutes rows if multiplied from left, and the columns if multiplied from the right. Okay, so now let's check with the normal matrix by matrix multiplication here. Let's say we were meant to do just normal matrix by matrix. So 0, 1, 3, sorry, 0, 0, 0, 0, 1 multiplied by 2, 3, 7. Okay, so that row dot multiply this column is going to be 7 here. First row, second column, this is going to be 5, and third, this is 9. Second row, first column, so going to everything is 0 except for 3 here. Here we have 6, and here we have 8. And then the third row, first column, we have 2. Third row, second column, we have 1. Third row, third column, we have 4. So as you can see, yes, they are the same. Is that okay? So 5. Yeah, this is the same. Let's continue with the following definition. Okay, so the elementary reduction matrices, if you remember in chapter 1, okay, Gauss method, the elementary reduction matrices, okay, the elementary reduction matrices are simply just elementary matrices. Okay, you can just say, or just elementary matrices result from applying a single Gauss operation to an identity matrix. So you will see this is a very beautiful definition. Okay, it shows us how to use these elementary matrices we have seen so far. Okay, how we can use them to be able to get a matrix in its echelon form and its reduced even in its reduced echelon form. Okay, so let me give you the formal definition. It results from applying a single Gaussian operation to an identity matrix. Okay, so what does it say? Let's see clearly here. So if you take an identity matrix, okay, and you multiply any row by k, okay, you will get a matrix Mi, okay, let's call it Mik. Okay, for k, being different from 0, we are going to call this new matrix Mi. Okay, so number 2, if you take an identity matrix and you swap any two rows, y, j, okay, you will get a new matrix. This is going to be a permutation matrix. Okay, let's call it Pi, j, P for permutation, M for multiplication, okay, K for K, being different from 0. And the last Gauss operation is K if you do row combination, so K times row I plus row J, okay, will give us a Cij, C for combination, okay, K for K being different from 0. And you will see this in action in the next video where I will do a tutorial, okay? I will show you. Just bear with me. Number 10, let's have a look at this lemma, 10. Okay, 10. We have matrix multiplication can do Gaussian reductions. We have just seen it shortly. So matrix multiplication can do Gaussian reduction. Gaussian reduction. So if H, okay, we have a H, okay, we multiply it by K row I, we will get a new matrix G, okay, then the matrix Mi that we have just seen, Mi of K multiplied by H is going to be equal to G. Don't worry, I will show you shortly in the tutorial, okay? If we have a matrix H, okay, and we swap any two rows, I and J, row J, to give us a new matrix J, then we got that by multiplying P, permutation, P, oh yeah, Pj, here I should have no K here because there is no multiplication. Here is for I being different from J. Okay, this is so for I being different from J, here K different from 0 and I being different from J as well. So here then we have P times H will give us J, will give us G. 3. We have if we have a H, okay, and we do linear combination row I, K row I plus row J to get a matrix G, then okay, Cij of K times H equals G. Okay, so I am going to finish this tutorial with the following corollary. Then in the next video, sorry, I'm going to finish this lecture with the following corollary, and then in the next video we will do a tutorial. Okay, we have covered a lot of theories today, so okay, so corollary. Okay, this is very beautiful one. I love it. It shows how we can perform Gauss's method using these elementary matrices for any matrix H. There are elementary reduction matrices elementary reduction matrices R1, R2, okay, Rn, this is Rn, such that R, this is R, not Rn, R small R times R minus 1 times, okay, dot times R1 multiplied by H is in reduced echelon form. So basically what we are going to do in the next video, the tutorial, is we will be given a matrix and we will be multiplying that matrix by elementary matrices so that at the end we can get an identity matrix, or in a reduced, we can get a reduced echelon form matrix, okay, an identity if that is a square matrix, of course, and it is non-singular, but we are not guaranteed the identity. So what we want is we will be given an original matrix. We will multiply that matrix by elementary matrices, okay, so that at the end we can get a reduced echelon form matrix, okay. So this is very beautiful, very interesting. It's a bit long, tedious, but it's very beautiful, trust me. So I'm going to stop at this lecture here, and I will see you in the next video for the tutorial, okay. Thanks.